Let us next consider the concept of a group. A set of elements A, B, C through G comprises a group G if the following axioms are satisfied. The product C of any two elements A and B of G, denoted by C is equal to AB, must be a unique element which also belongs to G. Among the elements of G, there must exist an identity element E, which when multiplied by any element A of the group, leaves the element unchanged. That is, EA is equal to AE is equal to A. For every element A of G, there must exist another element D also belonging to G, such that AD is equal to DA is equal to E. D is referred to as the inverse of A and denoted by A to the minus 1. The order of multiplication of 3 or more elements of G does not affect the result, i.e., multiplication is associative. A times BC is equal to AB times C. If the elements of G are symmetry operations, then we have a symmetry group. In the area of spatial structures, the commonest symmetry groups are the CN groups with rotation elements only, the CNV groups with rotations about a vertical axis as well as reflections in vertical planes, and the DN and DNH groups with dihedral symmetry. In this slide, we see a square configuration with C4V symmetry. This has 4 rotations and 4 reflections, and the hexagonal configuration with C6V symmetry. This has 6 rotations and 6 reflections. Here we see 3-dimensional configurations belonging to the dihedral groups D6H and D4H respectively, which have additional symmetry elements of reflection in the horizontal plane, rotations about the horizontal axis, and inversion in the center of symmetry. There are also the tetrahedral, octahedral, and icosahedral groups with more complex symmetries. Central to the application of symmetry groups is the concept of an idempotent. Idempotents Pi of a symmetry group are linear combinations of its elements which satisfy the relation Pi is equal to Pi, and Pij is equal to 0 if I is not equal to j. By operating on vectors of the space V of the problem, an idempotent Pi nullifies every vector which does not belong to the subspace Si or V. Thus, out of all the vectors belonging to the group invariant subspaces S1, S2 up to Sk, the operator Pi selects all vectors belonging to the subspace Si and therefore acts as a projection operator of the subspace Si. For example, idempotents of groups C2V and C3V, which describe the symmetry of a rectangle and an equilateral triangle respectively, are as follows. So for group C2V, we've got 4 idempotents, P1, P2, P3, P4, which you may think of as operators for the subspaces of symmetry, 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 antisymmetry, antisymmetry, symmetry, and antisymmetry, antisymmetry. And for group C3V, we have got 3 idempotents, P1, P2, and P3. As you can see, these are all linear combinations of the symmetry elements making up the group. The process of applying idempotents to the n functions of the problem has the effect of decomposing the vector space of the problem into a number of independent subspaces of smaller dimensions. The number of subspaces that are generated is equal to the number of idempotents associated with the symmetry group in question. Let the dimension of subspace Si i.e. the number of basis vectors spanning the subspace, be denoted by Ri. If the total number of subspace of the problem is K, then R1 plus R2 plus up to Rk is equal to N. In free vibration analysis, applying an idempotent Pi to each of the n functions describing the motions of a system with n degrees of freedom yields n symmetry adapted functions for subspace Si, from which a set of R independent symmetry adapted functions may be selected as the basis vectors of the subspace. If we follow the flexibility approach, the Ri by Ri flexibility matrix Fi of each subspace Si is derived by writing down the displacements at each of the Ri basis vector locations caused by the application of a set of unit forces at all the nodes associated with a given basis vector, while the loads of all other basis vectors are not loaded. This allows a smaller eigenvalue problem to be set up for each subspace. The symmetry adapted mass matrix Mi, which is an Ri by Ri diagonal matrix, comprises the values of the mass at each representative node of the Ri basis vectors. The vanishing of the determinant in the first equation yields the R eigenvalues of the subspace in question. The subspace eigenvalues are also the eigenvalues of the original problem. In this way, all the frequencies of vibration of the system are obtained. The second equation allows the subspace eigenvectors to be evaluated by substituting each obtained eigenvalue into the equation. Subspace eigenvectors are, of course, r-dimensional. To transform the subspace eigenvectors to n-dimensional eigenvectors in the space of the original problem is only a very simple final step. To illustrate the benefits of group theory, let us consider the vibration of double-layer space grids. Here are some symmetric configurations of typical double-layer space grids. The triangular grid has 10 nodes in the lower layer, 3 of which are supported, and 6 nodes in the upper layer. This gives a total of 13 degrees of freedom corresponding to the small vertical motions of the 13 unsupported nodes. The configuration belongs to group C3V. The hexagonal grid has 19 nodes in the lower layer, 6 of which are supported. The upper layer is 24 nodes. Thus, we have 37 degrees of freedom corresponding to the small vertical motions of the 37 unsupported nodes. The system belongs to group C6V. This rectangular grid of square-on-square offset configuration has 35 free nodes, i.e. 35 degrees of freedom, and belongs to symmetry group C2V. Finally, we've got a square grid, also of square-on-square offset configuration, with 21 free nodes. It belongs to the symmetry group C4V. Applying the idempotence of the symmetry groups in accordance with the procedure explained earlier, we reduce the vector space of each problem to a number of subspaces spanned by basis vectors in the form of symmetry adapted freedoms. Here are the results of the decomposition. For the triangular grid belonging to symmetry group C3V, the results show that subspaces S1, S2, and S3 have 4, 1, and 8 basis vectors respectively, which all add up to the 13 degrees of freedom of the grid. The symmetries of the subspaces are evident when the basis vectors are plotted. So in A, we've got the basis vectors for subspace S1. In B, basis vector for subspace S2. And in C, 8 basis vectors for subspace S3. In this plot, the solid dots denote downward movement of the nodes, while the small rings denote upward movement. For the hexagonal grid, which belongs to symmetry group C6V, subspaces S1, S2, S3, S4, S5, and S6 of the problem are found to be of dimensions 6, 1, 4, 2, 12, and 12 respectively, which all add up to the 37 degrees of freedom of the grid. The plots of the basis vectors of the first 4 subspaces are as follows. So subspace S1 has got 6 basis vectors. Subspace S2 has got only 1 basis vector. Subspace S3 has got 4 basis vectors. And subspace S4 has got 2 basis vectors. The last 2 subspaces, S5 and S6, are associated with 2-dimensional irreducible representations. We have not plotted the basis vectors for these. There are too many, but we note that only 6 distinct frequencies, not 12, need to be computed for each subspace. For the rectangular grid, which belongs to symmetry group C2V, subspaces S1, S2, S3, and S4 are found to be of dimensions 11, 7, 9, and 8 respectively, which all add up to the 35 degrees of freedom of the grid. Finally, for the square grid, which belongs to the symmetry group C4V, the associated subspaces S1, S2, S3, S4, S51, and S52 are found to be of dimensions 5, 1, 2, 3, 5, and 5 respectively, which all add up to the 21 degrees of freedom of the grid. To show the results of subspace modes more clearly, let us consider a single-layer square plane grid with 16 nodes experiencing small vertical motions. The square configuration belongs to symmetry group C4V, but we will use the simpler group C2V for the analysis. Applying the 4 idempotents of symmetry group C2V to the 16 nodal freedoms of the grid results in 4 basis vectors for each subspace, which when plotted look like this. So in A, we can see the basis vectors for subspace S1, in B, basis vectors for subspace S2, in C, basis vectors for subspace S3, and in D, basis vectors for subspace S4. After formulating the eigenvalue problem for each subspace, we solve for the eigenvalues and eigenvectors for each subspace and eventually obtain the modes of vibration of the system as follows. So in A, we see the modes for subspace S1. In B, the modes of vibration for subspace S2. In C, the modes of vibration for subspace S3. And finally in D, the modes of vibration for subspace S4. Notice that modes belonging to the same subspace have got the same symmetry type. In general, qualitative benefits of the group theoretic approach include the following: prior appreciation of all the possible symmetries of the modes of vibration, prediction of the number of modes of a given symmetry type, identification of modes associated with the same frequencies, prediction of nodal lines and stationary points of a vibrating system, and untangling of unclustered frequencies. In conclusion, this presentation has outlined the basic concepts of group theory as applied to problems with symmetry in structural mechanics. We've also explained the key steps of the group theoretic computational procedure by reference to free vibration analysis. Not only does group theory reduce computational effort, but it also affords useful insights on the vibration properties of the system before any detailed computations are performed. Thank you.
Okay, thank you very much for your presentation. And okay, right now is okay. So thank you very much for this presentation, and I consider paper for open for a discussion. Any questions? Okay, so I have one. What's the main advantage of your approach in vibration analysis comparing to others?
Oh, there are several advantages. Can you hear me, Chair?
Yeah. Yes. Okay. Yeah, we can hear you.
Okay, so there are two types of advantages, actually. The first one is the computational advantage, where, through the vector space decomposition, it means you reduce the computational effort, quite a lot. So you can imagine if I've got a large eigenvector problem and it is reduced to a series of smaller problems, then the effort required to extract the eigenvalues and also in turn to obtain the eigenvectors will be much less. So yes, that's one direct advantage, but for very, very large scale problems, it also gives you the opportunity to use parallel processors, to actually tackle the decomposed problem. So that's yet another advantage, which applies for very, very large scale problems. The second type of advantage, I touched on that towards the end, is qualitative in nature. So it means if you're studying systems such as this, you can actually do so more effectively. You get insights without going into any detailed calculations before you do that. For instance, you can predict the existence of multiply occurring frequencies, also the type of symmetries which are associated with modes which repeat themselves. You can predict various other physical features such as the existence of stationary points, the existence of stationary lines or stationary planes, even before you start the detailed calculations.
Okay, thank you very much. Do we have the question from MSAs? Yeah, okay. Professor Kawaguchi has one question. So Professor, please.
Okay, can you hear me?
Yes, we can hear you.
Okay. Yeah, thank you very much for the very clear lecture about the basic of the theory, group theory. And I understand probably the early person who applied this theory to the structure was Sattinger in 1960s. And later in 1980s, Professor Ikeda in Japan also applied this theory to the buckling problem of space frames. And more recently, we can find many people have already applied this theory in a very convenient manner to the structural engineering problems. So my question is, how can we identify the symmetricity of the structure in the problem? For example, in your case, you have just explained the hexagonal, the symmetricity of the hexagonal, for example, structure, which is already determined by yourself. But is it possible to identify the correct symmetricity of the structure automatically, for example, by the computational program or something? Is it possible? That's my question.
Okay, can I answer that?
Yes, please.
First of all, I would like to acknowledge, the names which you mentioned. In fact, I'm, quite aware of the, pioneering work of people like, Sattinger, whom you mentioned. who also successfully applied, group theory to problems in structural mechanics. Keda also in Japan, and Murata, I think that was the colleague.
Yes, I know. I know.
Yes, Keda and Murata, yes. They both were also involved in these types of problems. But of course, their main focus was, instability, bifurcation problems. So the good thing about it is that the types of applications in structural mechanics has expanded, since that time, from problems involving bifurcation and stability to problems involving vibration and even the study of the kinematics of certain complex systems. So it's actually very pleasing to notice that the applications are expanding within the area of structural mechanics.
Yeah.
Now, to come to your question, how can we identify the symmetries? What has happened, with the simpler types of symmetries, one could simply identify those by inspection. So in a lot of practical systems, the type of symmetry is quite evident. So the structural engineer can easily, pick out the symmetry group and then decide, which symmetry group, to use in the computations. But what tends to happen also with the more complex, type of configuration, sometimes the symmetries are not obvious.
Yes.
So in those cases, you need a systematic approach to identify the symmetries. I can make reference to one paper, which I wrote. I think it was about 8 years ago now, where I attempted to give an algorithm, for the systematic, searching of symmetry properties in both two-dimensional systems as well as three-dimensional systems. So it's computationally very intensive. It's very, a lot of searches are required in order to identify all the symmetries. So that type of formal approach would only be justified in the form of very complex types of symmetries. Otherwise, I would say, simply use, inspection.
Right. Thank you very much. So I understand that. So you have already proposed some kind of algorithm or systematic approach.
It is actually an algorithm, which which involves very careful steps, so that you don't miss out any symmetries. And I should also say, I'm not the only one. There are also a few other people around the world who have also contributed to the efforts to develop such algorithms.
Yes, as you have mentioned, so the theory, how to apply this symmetricity is already well developed. So I think that say how we can find out the symmetricity in the structure or any structure is very important. So thank you very much for the information about your work. I try to find out it. Thank you very much.
Thank you for your question. Thank you.
Yes, thank you very much for the question and for discussion. And Professor Zingoni, we still have like 1 minute, and maybe you can tell us something about and advertise your conference in Cape Town that would be held in Cape Town next year. So it's time for you to advertise it.
Oh, thank you very much. That's very kind of you. I do not expect you to give me that opportunity. But anyway, we're going to have this conference in September, which is SEMC 2022, which will be the 8th edition, in the series, since the first one in 2021. So we are expecting, participants from all sectors, within structural engineering, within structural mechanics, materials and various fields. COVID-19 permitting, of course. So at the moment, the plan is to have that as a face-to-face, conference. But if that turns out to be not possible, then we've also got a plan B to, is something similar to what you are having here at this conference in Poland, a hybrid event of some sort. So yes, I would like to invite you to, to participate if you can. We've always had a very strong representation from Poland, if I might say, And one of our very important participants at these conferences have been Professor Jan Obribisky. He holds the record of having attended all 7 conferences in Cape Town. So we very, very much appreciate that and have got very fond memories of his participation in Cape Town. Thank you.
Okay, thank you very much. I feel invited. And as you know, I'm gonna be there because I have sent the abstract, so we can meet in Cape Town next year. Thank you for your presence. Thank you for your presentation, and once more, thank you very much.
Thank you.
Okay, so the second lecture, it's a work done by Dr. Jarosław Benz, Professor Ewa Błazik-Borowa from Lublin University of Technology, and with my the team is also with my dear friend Jacek Szer from Łódź University of Technology. I guess the presenter will be Dr. Jarosław Benz. So the floor is yours.
Thank you, Mr. Chairman. So the theme of the presentation, the title of the presentation is Analysis of the Harmonic Excitation of Scaffolding Structures. My co-authors have already been presented. We are from Poland. I'm going to talk about scaffoldings. Scaffoldings were presented yesterday by my colleague Ewa Błazik-Borowa. These are lightweight structures. They are temporary structures mainly used at construction sites. And at the construction sites, they are prone to vibrations that are excited by the equipment present at the construction sites, and also by the workers working on the decks of scaffoldings. We have been working with facade frame scaffoldings. One of such scaffoldings is here. We have a frame, a series of frames, and they are connected in a plane, usually in a plane. As light structures and the structures that are many times assembled and disassembled, they are prone to vibrations of low frequencies. The frequencies that we have identified on such structures are, let's say, from 1 to 10 hertz, sometimes even 15 hertz. So these vibrations can induce some displacements, some accelerations, and even some effort in coming from the forces in structure elements. The purpose of this analysis was to find out which frequencies mostly affect the scaffolding and what areas are affected by the vibrations, and to get the easiest analysis to find out the results. We have decided to use the excitation force of sinusoidal harmonic character. So we have applied just a single sinusoidal force acting on the scaffolding in the selected points. We have applied this force changing in time at one point to the medium-sized scaffolding. So far, we have many models, finite element method models built already, and we are going to test it on other scaffoldings as well. The model is presented here. We have a scaffolding which is roughly 25 by 25 meters. This finite element model was built with frame and shell elements. Shell elements are the platforms with also frame elements here. And there was also a cladding mesh, which is not seen in this picture. The model has been built and it was verified on the basis of measurements in nature. It was really built scaffolding here in Łódź. And we have measured and calculated natural vibrations and compared them. To make this analysis, dynamic analysis, I have found 121 characteristic points. We have numbers of finite element model nodes here presented. These are the nodes that are in the frame, in the outer pipe of the frame, and in the connection with the horizontal beam of this frame. First, we calculated the natural vibrations and natural frequencies of this scaffolding. The first natural frequency was just above 2 Hertz, and we have found that first 50 natural frequencies are in the range of this 2 to about 12 Hertz. So the spectrum of natural frequencies is quite compact. Many frequencies fall in this range. We have presented mode shapes here in this picture. As you can see, the first mode is the global mode shape of the scaffolding, but some of the other mode shapes affect only a part of the scaffolding, which points are prone to the vibrations, more affected by the vibrations. We have calculated also force vibrations. This is the main theme of this presentation. So we have applied just a single harmonic force in one of the selected points in a single analysis, and we have made this analysis at one time with one force, and we have observed the results, displacements in horizontal vibrations along the facade, perpendicular to the facade, and vertical vibrations. The analysis time was 10 seconds. Here are some other parameters. We have used direct integration to find the results. The frequencies were ranging from 1 Hertz to 12 Hertz. I have decided that every 1 Hertz, so there were 12 cases in each analysis. Analysis parameters 100 of a second time step, the number of time steps 1000, and the excitation force was active in the first half of this analysis. I have used the typical logarithmic decrement of damping for this structure. This was based on measurements. As a result, we obtained a series of displacements in 121 points, and each analysis here presented some just exemplary graphs. We have a very big number of these graphs, and it was hard to observe all of them. So I have presented them in 3D pictures. This is the surface of the scaffolding. We have height here. This is height. Yes, this is this dimension. This is presented here. Is the length of the scaffolding, and the vibrations are induced in this direction along the scaffolding, and the source of vibrations was also along the scaffolding, and in this point just one presented here when the force was applied. So we have the picture of 1 to 12 Hertz in one direction, similar pictures in another direction. So we have the excitations along the facade, horizontal excitation, but this time they are presented vibrations perpendicular to the facade, and similar cases for vibrations observed in vertical direction, also with excitations along the facade. So very many pictures. I'm afraid there is no time to present them all. We have another directions of excitation and similar pictures in every directions and for every analyzed frequency of excitation. Maybe I will skip the next some pictures and present these results all together in this picture, but for another node. This is a node at the bottom of this scaffolding. So maybe I will come to some conclusions. First, we have observed that the horizontal vibrations are the ones that are most propagated. The vertical vibrations are the least propagated. They are propagated at the lowest level. Of course, frequencies that are close to natural vibrations are more excited, and they propagate along the whole facade, and the higher frequencies at 10 and more hertz are not that much propagated, and they are at the small area of the observed at the small area of the scaffolding surface. Sometimes the direction of excitations was completely different from the ones that we observed as excited ones. When we tried to move along the facade horizontally in the facade of the scaffolding, sometimes we observed vibrations perpendicular to the facade of the scaffolding. It was just a common. A very important factor of propagation of vibrations is how the scaffolding is anchored. So if, of course, we try to force the vibrations in the point where there is an anchor, then it's just obvious that when we try to move where we have a support, then we don't get the vibrations. There are no directly supported nodes, but we are just outside the facade, so we have some, let's say, spring support. So every time we had some amount of vibrations. So some outlook we have in our project, we have made 120 models of scaffoldings of small, medium and large sizes. So I will try to make this analysis for maybe not all of them, but some of the selected scaffoldings, and also some damping parameters, so logarithmic decrement of damping. I will use other values and see if something is changed. So thank you very much.
Thank you very much for this interesting presentation, and the paper is open for a discussion. Professor Walentyński.
I have two questions. First of all, how have you modeled, because vertical and horizontal bars are not connected in the same plane? So have you taken into account that fact in your model? Yes, but it is connected with some, it will change the solution. The second is that connections in scaffoldings are not exact. They are not welded or connected with pre-stressed bolts, but only made by humans. So it is connected not only with different stiffness, for example here, but also with higher logarithmic decrement of damping, because this. And the second, as I understand from your drawings, you have upper part of the structure was not connected to the facade, because usually, and because of that, it was possible, because normally it is requirement that the displacement in direction counter facade is impossible, because in each level this scaffolding should be connected to the facade.
The first question, I think we have a connection in one plane. So the point that I have applied the force was this point where we have a frame, and this is a point where the outer pipe of the frame was connected with the horizontal bar of the same frame. So this is the point where I put the load, and I have read bracing not. So we have not used an accent. No, I don't think so. So maybe my colleague who has built this model would know.
I'm not sure I understand. Your question about platform or bracing? We didn't use for eccentric, but because all elements are very slender, and but in this moment, when we calibrate or verification of model, we try to suit the free vibration and natural vibration, and sometimes we change, for example, the anchor were deleted, because I think that it is answer the next questions. So we sometimes the anchors were deleted, or sometimes we inserted spring as support.
Okay, thank you for this discussion. Thank you for your presentation. I don't have more questions, but I have one comment. You guys are the only team that I know that deal with scaffolding structures, and I consider it as extremely important, because we know that it's somehow touches the things like with the safety of people and so on, so on. So I really appreciate your work, and I just want to say that you guys do a terrific job. Thanks for that. Thank you very much. Next presentation is from the Gdańsk University of Technology, from Professor Jarosław Górski and his I guess PhD students, Przemysław, Sorn, Mateusz, Sondej. I just want to say a few words about Professor Jarosław Górski. Unfortunately, he, taking into account the situation with COVID, he couldn't be with us today, but he wants to say hello to everybody. I know he's up there with his computer. So the one who delivers the presentation will be Przemysław Sorn. So it is your time.
Hello, my name is Przemysław Sorn. Thank you, Mr. Chairman, for giving me a voice right now. As it was described, I am PhD student of Mr. Professor Jarosław Górski. I'm working in KB Pomorze as a project manager. Today, I would like to give you a presentation about sensitivity of the stresses and deformation of underground tanks to non-standard actions. The tank that was taken in consideration is the real tank that was built around 7 years ago, and right now was put for operations. And during this time, during these 7 years, it's already working. At first, I would like to give you some information about the legislation in European Union for the pressure equipment. all the pressure equipment needs to comply with the pressure equipment directive. The directive gives us the essential safety requirements that need to be met during the design and manufacturing process and construction. To comply with the directive, you can implement all the harmonized standards, like the standard shown on the picture, the PNN 13445. It's a full set of the standards. Or you can also use local standards like WDT or ASME standards, for example. Standard procedure for this kind of construction is to use the design by formula methods. It's, to simply put it, it's not a method based on finite element methods, but it's based on putting or using a correct formula for calculating the minimal thickness of the construction. This is the geometry of the tank. The full length of the tank is 72.6 meters. The diameter is 5.6 meters. Thickness of the shell is 28 millimeters with the material P355 NL2 grade. It was designed for the pressures like 1.61 megapascal and the situation for full vacuum to occur minus 0.1. At the bottom of the chart, you can see two models that we considered. One is without the stiffeners, and the second one have stiffeners included. Also, we analyzed only the parts that is long around 33.5 meters and is located between the stiffeners. Yes, between the stiffeners. What type of the analysis we focused only on, mainly on the linear backlink analysis. Typical loads for the shells according to the Eurocode 3 are the internal pressure normal to shell, internal pressure longitudinal direction, and the combination of the previous two. And it is important to say that the typical force combination for the pressure equipment is the last one. At the beginning, we wanted to check how what is the influence of each of the loads on the cylinder. We made for each of those load situations, we made different models. We wanted to check how the critical load or critical pressure behaves when we limit the thickness on the all part of the cylinder. What we can see, of course, it have a very huge impact, but what you can see is for the longitudinal pressure, the values of the critical pressure is higher than the design pressure in most situations. So the pressure, so the cylinder is not so for this kind of load when analyzed separately is not so much important. But if we see that in a situation when we apply only a nominal pressure and the situation when the normal and longitudinal pressure is applied simultaneously, we see that the reduction of critical value of pressure is around 18%. On the next slide, we wanted to check what is the how the shell behaves when we model some local imperfections. The imperfections was modeled on the reduction of the thickness on the angle of alpha degree, we analyzed 3 different degrees, 30, 90, and 180 degrees. Each of the line describes it. Also, we checked it for different thicknesses like 28, 25, 20, 15, and 5 millimeters. It is important to say that the reduction by 3 millimeter thickness from 28 to 25 millimeters on the 30 degrees angle reflects in 4.6% of critical pressure. So this is between this and this point. Also, at some point when the reduction of thickness is very significant, the nature of the bifurcation on EG value takes a local nature. So we only lose stability on the locally. On this chart, those are the results of the critical pressure, how it changed depending on the number of stiffeners that we put inside. First graph represents the internal pressure normal to Szer and the combination of the normal pressure and longitudinal pressure. The bottom one represents the longitudinal pressure. And the nature of the behavior is similar, but what we can observe, increasing the stiffness from 0 to 7 reflects in rising the critical pressure for longitudinal load by 6%. But if we consider the normal to shell pressure, we can see that the rise of the critical pressure is 7 times. Now, short comparison to the Eurocode 3. The constraints was done on the edges, the H1 and the H2, so on each end, on the boundary condition B1, so it's a clamped situation. We see that the difference between the model and the results from the Eurocode are around 3.5% difference for the longitudinal load and 5.5% on the situation when we consider the normal to shell load. Also, it is important to say that the Eurocode doesn't give any conditions when the tank is underground. So the real boundary conditions are different from what was taken into account during the analysis, because we have a situation when the tank is supported on the bottom of its shell, not on its ends. And last slide is the comparison to the pressure vessel standard. The standard, if we design it according to the pressure vessel design standard, then we have a stiffener spaced between around 4.3 meters. They are T-shaped with the web of 22 millimeters or 28 millimeters of length. It is called the heavy design type. We see that for the ground load is around 0.16 megapascal. Internal pressure for full vacuum situation is 0.1 megapascal. So total pressure applied to the cylinder is around 0.26 megapascals. That represents the red line. And from our analysis, we see that the number of stiffeners needed in this kind of situation, in this kind of load, on this value, is one stiffener. But from some reasons, the standards applied much more. This is for future potential subject for manufacturing cost optimization in design phase. We need to clearly analyze it and see why the standard proposed so stiffeners, so why the standard proposed so many stiffeners. And the conclusion. Firstly, the longitudinal forces have huge effect on shell stability when analyzed together with other forces, for example, internal pressure like full vacuum situation. Cylindrical construction of pressure vessel are fragile to local thickness imperfections. In some cases, local stability loss can occur. Syncofacial stiffeners have huge impact on stabilizing pressure vessel shell construction. Eurocode 3 doesn't provide the values of design factors for cylindrical shells in situation where vessel is supported on elastic ground bearing, and the pressure vessel code proposes more stiffeners than applied analysis suggests. Possible cost optimization after more detailed analysis is applied. Thank you very much. Is there some question from your side, and I'm ready to answer.
Okay, so we have a time for just one question or one comment. Anybody? Okay, thank you very much.
Thank you
for this interesting presentation. And we have one more presentation for session number 1. This is a presentation from our technology, from Professor Marcin Kamiński and his PhD student, Bredow.
Thank you, Mr. Chairman. So firstly, let me introduce myself. My name is Bredow. I am a PhD student here at Łódź University of Technology. My scientific supervisor and also co-author of this work is Professor Marcin Kamiński. Today, I would like to present our recent work regarding random response of steel hull subjected to the dynamic excitation by the generalized iterative stochastic perturbation technique. Firstly, I will make a general, very brief overview of the investigated structure. Then I will say a few words about the dynamic analysis and methods of integrating equations of motion involved in this work. Later on, I will discuss the probabilistic approaches, most importantly the stochastic perturbation technique, and also taken other referential techniques. Later on, very briefly chosen numerical results and also stating some final remarks. In this work, the single aisle steel hull has been taken upon as an exemplary object. Its main frames has been modeled as tapered I-beams and gable frames as rectangular hollow sections. Entire numerical model has been introduced into the abacus system, so it gave an opportunity to introduce the B32OS finite beam elements. Those are 3-node quadratically formulated elements which may involve for those tapered I-beams the warp of its cross sections. I believe this is worth to mention that this particular structure has been recently designed and erected in central Poland by the Commerzbank company, to which I am also professionally related. And this gave an opportunity to very accurately interpret and introduce the geometry and assignment of cross sections into the finite element model in abacus. As for the dynamic analysis, this structure has been subjected to the dynamic wind excitation in 10 minutes time interval, and this wind velocity spectrum undergo further calculations followed by the Eurocode 1 statements, so that the dynamic wind pressure in 10 minutes time interval has been found, including the orientation and the orography of the terrain of this real structure. As for the methods of integrating the equations of motion, the Hilbert-Hughes-Taylor algorithm has been involved into the abacus software. The bold letters M, C, and K, of course, stands for mass, damping, and stiffness matrices, respectively. And in this method, the nodal displacements and velocities at the subsequent time step of calculations are being assessed based on the nodal displacements, velocities, and accelerations at the previous time step. Those coefficients beta and gamma are directly correlated with parameter alpha, which in this method stands for numerical damping. And in this work, it has been assessed that the maximum numerical damping is involved equal to -0.3. Now, The 4 different uncertainty sources has been taken upon in this work of both environmental and mechanical nature, like the cover of the thickness of snow cover on the roof, the wind velocity itself, also the thickness of webs and flanges, or in general of cross sections of those finite elements, and also the elastic moduli. All of those uncertainty sources has been considered separately, and now for all desired structural responses like displacement states or stress states in this 10 minutes time interval, in fact, each discrete structural response at current time step is being described by the 11 different realizations of considered uncertain parameter in its domain. So that at this point, the weighted least squares method approximation of some polynomial structural responses takes place for every desired structural response at each time step of recovered calculations. So now, at this point, the probabilistic approaches takes place in self-written algorithms in algebra system Maple. Firstly, and most importantly, the stochastic perturbation technique, and also 2 referential approaches, namely Monte Carlo simulations and semi-analytical approach. It has to be stated at this point that those input uncertainties has been considered of Gaussian distribution and their input coefficient of variation is equal to 0.1. And now some chosen exemplary results. In this case, the SLS state has been considered of horizontal displacements of the very top node of columns, and it has to be said that also the direction of wind excitation is in the plane of those main frames. Firstly, one may notice that stochastic perturbation technique maintained remarkable accuracy compared to referential approaches as for those expectations. Also, those output coefficients of variation maintained satisfactory accuracy when contrasted the stochastic perturbation technique to referential approaches. And from these graphs, another remark can be made that firstly, the structure exhibits different sensitivity towards those considered parameters, as the output random dispersion of those horizontal displacement regarding profile thickness is larger than referring to, let's say, elastic moduli or other contrasted or other considered parameters. Another thing that might be mentioned at this point is also that the output random dispersion is generally smaller than the input one, which has been equal to, as I said before, 0.1. Accurately assessed coefficients of variation and also expectations allowed also to calculate the reliability of the structure regarding Euro-zero statements. And general remark here is that overall, in SLS state of horizontal displacement, this structure exhibited quite large reliability, as the reliability index never dropped below 10. Similar series of tests are being presented here regarding some stress states at the very top node of the ridge of those tapered beams. And one may notice that once again, stochastic perturbation technique recovered very accurate approximation of expectations and coefficients of variation. And in here, at this point, the thickness of snow cover is the most sensitive parameter. Nevertheless, similar observation, the output coefficients of variation are in general smaller than the input one, which has been equal to 0.1. One another remark, very similar calculations has been performed in robot software with the very same integration by the Hilbert-Hughes-Taylor method and the very same numerical damping. And basically in here on those graphs by blue color, the internal forces recovered by some arbitrary node are being presented, and in orange, those recovered from abacus. One may notice that basically those discrepancies in between recovered responses in robot and abacus are marginal. Nevertheless, one additional value added to the work which has been performed and presented here, the output response in abacus also is able to recover the moment which is related to the warp. Nevertheless, this influence on general stress state of those tapered I-beams has been found marginal. So to conclude, firstly and most importantly, the stochastic perturbation technique returned similar responses and probabilistic figures as Monte Carlo simulations and semi-analytical approach, yet requiring much less computational cost, which I believe is crucial, especially in structural dynamics, when those probabilistic approach has to be taken at each time step of calculation. So a lot of samplings, let's say in Monte Carlo simulations, could have been done at each time step. So this stochastic perturbation technique implementation is, I believe, crucial. Secondly, the investigated steel Hall structure exhibits quite remarkable reliability when the SLS state has been considered, yet exhibiting different sensitivity towards those considered parameters. Also, as I have said before, this random dispersion of output responses has been smaller than the input one, which has been equal to 0.1. And additionally, the warp of those tapered I-beams has been found marginal when the Abacus numerical model has been compared to responses obtained in robot system. This is all what I had to say. Thank you very much.
Thank you very much. So it's time for our questions and the discussion. I have the first question. I just want you to ask, from where do you get the excitation function? From where you have adopted it? I'm asking because it's quite familiar for me and I couldn't find it in the references. So please answer.
Basically, it has been taken from the literature, and in definitely in full paper submission, such a reference should have been stated. Nevertheless, such wind excitation, it is worth to think of real data from this real location of the structure always, so that some meteor station could have also been the source of such a data in the future plans for other structures.
Okay, thank you for your answer. Anybody? Yes.
I have one question about the natural frequency of the system, because usually when we deal with dynamic analysis, full transient history of the vibrations of the system, we worried about structures where the natural frequency is less than one hertz. I suspect that in this type of structure, the first natural frequency is much higher. So that's my. Do you need such a detailed dynamic response in wind excitation? Thank you very much.
Thank you for this question.
Thank you for this question. This is a very important question. Basically, as you have said, this first frequency is higher than 1 Hertz, but basically we search for the method of implementation of stochastic perturbation technique in all types of slender steel structures like steel masts, steel hulls, and towers, let's say. And basically in this particular case, perhaps wind excitation might not influence significantly the structural vibration itself in this particular form. Nevertheless, we believe that this is important to verify and check all those possibilities which gives us this stochastic perturbation technique. So in this case, in fact, those dynamic wind excitation with this spectrum did not influence additionally those structural responses.
Just my comment as the co-author, maybe you've seen in Eurocode 0 that calculation of reliability index is mandatory for only 2 limit states. So practically there is no value to be compared for eigenfrequencies. That is the weakness of the Eurocode. So as the engineers, we can say pass. Thank you.
Okay, thank you very much for your questions, for discussion, and we have a time for a coffee. Let's have a coffee. Thank you very much.